Every hour, over 1 billion square feet of glass are produced worldwide. But only one of them has clothed a giant that pierced the sky. Imagine a building taller than 3 Eiffel Towers, covered in glass with an area equal to 5 football fields. This is the Burj Khalifa, a symbol of human ambition. But what if I told you that it all started with sand? And a secret recipe that is still kept under wraps? Watch until the end, because something will be revealed that you've never heard of before. A property that turns glass into a source of life in the very heart of the desert. Imagine this. Dubai, a city that grew out of the desert, decides to surprise the world. Sheikh Mohammed bin Rashid Al Maktoum, the ruler of Dubai, sought to transform his country into a global tourist destination and reduce its dependence on oil revenues. And so, among ambitious projects, the idea of building a tower taller than anything humanity had ever seen was born. Construction began in 2004, and on January 4th, 2010, the world held its breath as the Burj Khalifa, originally named Burj Dubai, officially opened its doors. The height? A staggering 2,717 feet. That's almost 3 Eiffel Towers stacked on top of each other. 163 floors piercing the sky. The cost of this giant, about $1.5 billion. And now let's get to the main point. It's glass attire. How do you dress such a colossal structure? After all, the exterior surface of the Burj Khalifa is covered with glass and metal, and the area of this glazing is, imagine this, equal to the area of 5 football fields, or, to be more precise, about 1,528,000 square feet. That's an incredible number, and each panel had to be not just beautiful, but also functional. Have you ever wondered what it's like to live and work behind glass in a place where the air temperature can reach 122 degrees Fahrenheit? It's a real challenge. Therefore, the architects and engineers from the American company Skidmore, Owings and Merrill faced an incredibly difficult task. They had to create glass panels that would protect from the scorching sun and unbearable heat, yet allow enough light to pass through, and offer incredible views of the Persian Gulf. This is a true engineering feat. So, how did they do it? Each glass panel of the Burj Khalifa is a complex multi-layered sandwich. The outer layer is glass-coated with a thin layer of metal. This coating reflects the sun's rays, preventing them from heating the interior. The next layer is an air gap, which serves as additional thermal insulation. And finally, the inner layer is strong laminated glass for safety. Imagine how well thought out every detail had to be. The production process of these panels is a story in itself. The glass for the tower was manufactured at specialized factories, particularly in Syria. Each panel underwent strict quality control. It was tested for strength, resistance to temperature fluctuations, and wind loads. And the winds up there, at that height, can be quite strong. Engineers developed a special window frame design capable of withstanding the extreme weather conditions of the desert. So, how does the creation of one of the more than 26,000 glass panels for the Burj Khalifa begin? It all starts with fire and sand. At the core of everything is ordinary quartz sand of the highest quality, soda ash, and limestone. But don't think it's that simple. The proportions of these components are a trade secret, the first step towards creating super strong and functional glass. This mixture is loaded into a giant melting furnace, the size of a small house. The temperature inside? Over 2,700 degrees Fahrenheit. It's a real inferno, where the loose mixture turns into a red-hot, viscous, dazzlingly orange lava. And then, one of the most spectacular stages begins. The float glass process. The molten glass mass is continuously poured from the furnace onto a perfectly flat surface of molten tin. Yes, you heard that right. A huge bath filled with liquid, silvery metal. The glass, being lighter than tin, spreads over its surface like oil on water, forming a perfectly smooth, impeccably flat sheet of a given thickness. No distortions, no defects. It's like a fiery river, slowly flowing and solidifying. Then this endless glass ribbon enters a long tunnel for controlled cooling, or annealing. This is a critically important stage. If the glass cools too quickly, internal stress will simply shatter it into pieces. Therefore, over a few hundred feet, the temperature gradually and very slowly decreases. This relieves the stress and makes the glass stable. Now we have a giant sheet of transparent glass. But for the Burj Khalifa, this is not enough. It's time to give it superpowers. The panels are sent to vacuum chambers for the application of a special coating. This is the heart of the technology. In an almost complete vacuum, using a process called magnetron sputtering, the thinnest layers of metals, most often silver, are applied to the surface of the glass. Layer by layer, atom by atom. The thickness of these layers is measured in nanometers. It's thousands of times thinner than a human hair. It is this coating, invisible to the eye, that will reflect solar radiation and ultraviolet rays, protecting the tower's interior from the desert heat. Incredible, isn't it? But the glass must also be safe. Therefore, it undergoes a tempering process. The glass sheets are heated again to a temperature of about 1,150 degrees Fahrenheit, almost to the softening point, and then sharply cooled with powerful streams of cold air. This thermal shock creates incredible internal stress. The surface is compressed, while the inner layers remain in a state of tension. As a result, the glass becomes 5 times stronger than ordinary glass. If such a panel does break, it will shatter into thousands of small, safe crumbs without sharp edges. And that's not all. Remember the sandwich? Now it's time to assemble it. They take 2 sheets of glass, one tempered with a solar control coating, which will be the outer layer, and one simply tempered or laminated, which will be the inner layer. A special spacer frame is installed between them, creating a hermetically sealed air gap. This air gap is a key element of thermal insulation. This entire structure, called an insulated glass unit, is sealed around the perimeter. That's it! A high-tech panel, ready to withstand winds, heat, and time, has been created. Each such panel undergoes dozens of quality checks. Lasers scan it for the slightest scratches, sensors check for air tightness and coating quality. Only after this does it get a one-way ticket to Dubai, to become part of the sparkling mosaic on the body of the giant. And now imagine the installation. How do you lift and install thousands of these heavy glass panels at a height of hundreds of feet? It was a real choreography on the construction site, where 12,000 workers from different parts of the world worked simultaneously. In total, 22 million man-hours were spent on the construction of the tower. Special cranes lifted the panels to the required floor, and then a team of highly skilled installers, like mountaineers, secured them to the facade. It was a job that required incredible precision, courage, and coordinated actions. An error at such a height is simply unacceptable. And so, panel by panel, the tower was dressed in its sparkling glass attire. Each element was part of a giant puzzle, perfectly fitted to its neighbor. And the shape of the building? It's not accidental. Architect Adrian Smith was inspired by the shape of the desert flower Hymenacalis, which grows in the region. The Y-shaped floor plan not only maximizes views, but also ensures the stability of the structure. And did you know that the glass of the Burj Khalifa has another amazing property? It collects condensate. In the hot and humid climate of Dubai, this is a real lifesaver. The condensate collection system gathers the moisture that forms on the glass panels and directs it to a special reservoir. This water is then used to irrigate the plants on the complex's territory. Imagine, about 15 million gallons of water a year are collected this way. That's a whole lake. The story of the Burj Khalifa is not just a story about the construction of the tallest tower. It's a tale of human ambition, of the courage to dream and bring those dreams to life. It's a story of how an oasis of technology and innovation can be built in the middle of the desert. Every glass panel that glitters in the sun is a testament to the incredible work of thousands of people who contributed their efforts to create this architectural marvel. So the next time you see photos or videos of the Burj Khalifa, remember this incredible story about how molten sand gives birth to glass, how it is transformed into high-tech panels, and how these panels, one by one, create a sparkling facade that has conquered the sky. It's truly impressive, isn't it? It's a story that inspires and proves, for human genius, nothing is impossible. The largest gasoline production plant in the United States is Marathon Petroleum's facility in Galveston Bay, Texas. It's a true giant, processing 631,000 barrels of crude oil every day. That's about 26.5 million gallons every single day, a staggering number. Let's dive into the atmosphere of oil refining production. It all began long before the era of hybrids, electric cars, and climate summits. Back in the days when America was still smoking and roaring, the world needed fuel, and Texas provided it by the spoonful. On the coast of the Gulf of Mexico, in the Texas city of Texas City, a decision was made back in 1931 to build a plant that would refine oil into liquids that make cars and airplanes roar. By 1933, the plant was operational. At that time, it belonged to Republic Oil, and a little later, it was taken over by Amoco, which eventually became part of British Petroleum. Those were wild times. Every day, a new record. Gallons of gasoline flowed like a river, and the plant gradually expanded. It survived World War II, the oil crises of the 70s, and even an explosion in 2005 when 15 workers died at a neighboring facility, a tragedy that forced a complete overhaul of safety in the entire oil refining region. Have you heard about it? And so, in 2013, the giant changes hands. Marathon Petroleum Corporation buys the plant. And they don't just buy it, they integrate it with their own refinery located nearby. Thus, a single gigantic system is born, the Galveston Bay Refinery, which since then has been processing over 630,000 barrels of crude oil every day. To imagine the scale, that's over 26 million gallons of fuel per day, and the complex covers nearly 1,000 acres. Over 1,500 people work there, not counting contractors and specialists who service the units. It's like a small industrial city, only instead of coffee shops, there are reactors instead of fountains, cooling towers, and instead of a park, thousands of pipelines. Galveston Bay is the pulse of the US fuel infrastructure. It operates 24 hours a day, 7 days a week, without stops or breaks. It's not just gasoline that's born here, they also produce jet fuel, diesel, fuel oil, petroleum coke, and even propylene for the chemical industry. Everything that can flow, burn, and work is squeezed out of every drop of crude oil. Interestingly, the plant's location is strategic. The nearby port allows for receiving tankers from all over the world and a network of pipelines and railways for sending products all over America. Roughly speaking, if you're filling up your tank somewhere in the US, there's a chance that at least a drop of that fuel passed through the furnaces of Galveston Bay. And although the world is changing today, and green energy is being talked about from every microphone, the Galveston Bay Refinery is not giving up its position. Marathon Petroleum is investing hundreds of millions of dollars in modernization, filtration, and reducing harmful emissions. Because as long as the planet is still roaring with engines, this Texas giant remains at the heart of the American highway. We are heading to a territory where it doesn't smell of flowers, but where pipes roar, signal lights flash, and black gold is turned into gasoline. Galveston Bay Refinery, one of the largest plants in the US, and production there begins not with the push of a start button, but with thousands of miles of logistics, pressure, and thermal alchemy. The first drop of oil in this story doesn't yet have the smell of gasoline. It's in its raw form, viscous, dark, with impurities, water, sulfur, and metals. It's delivered by tankers through the port of Texas City, or pumped through pipelines that stretch for thousands of kilometers. This plant can receive over 1 million barrels of crude oil per week. That's an insane amount. The oil goes into huge tanks, so-called crude tanks. Each such tank can hold 500,000 barrels. Imagine that. That's more than 20 million gallons. Here it is stored for several days, where it settles and is heated to a temperature of about 140 degrees Fahrenheit to reduce viscosity and facilitate pumping. Next, the oil goes through desalters. These are special units that remove water, salts, and mechanical impurities. Because salts are death to metal reactors, they cause corrosion and form dangerous deposits. Here, the oil is mixed with fresh water and electrical energy, creating an emulsion that forces the impurities to separate. This is, essentially, industrial cleaning. After this, the main stage, the atmospheric distillation unit. A tower 230 feet high, where oil heated to 650 degrees Fahrenheit is fed in, and vapors rise to the top. And here the magic begins. Heavy fractions like diesel, kerosene, and fuel oil settle at the bottom, while lighter ones, the gasoline fraction, naphtha for petrochemicals, rise to the top. You can imagine this tower as an oil elevator, where each floor is a separate product. The temperature in the column plays a key role. At each height, its own condensation point. Heavy components stop faster, light ones fly further. All this works in real time with control over every degree and every drop. But no, this isn't gasoline yet. What has been collected are raw fractions that are then sent to other units. Vacuum distillation, catalytic cracking, hydrotreating, and only then to blending. That is, mixing to meet the standards for gasoline, diesel, and jet fuel. By the way, gasoline itself is not a single component, but a mixture of dozens of fractions that are chemically and physically stitched together into a precisely calibrated formula, with an octane number, ignition temperature, volatility, aromatics, all according to standard. But let's go back. After the atmospheric tower, many heavy fractions are sent to a vacuum column, where they are distilled under reduced pressure, so as not to burn them to a crisp. From there come components for lubricants, bitumen, and even raw material for plastics. Then even deeper, catalytic cracking, where molecules are literally broken into smaller ones, turning heavy fuel oil into light gasoline. And only when this black magic is complete does the collection of fractions, mixing, adding additives begin, and at the end, storage tanks with the finished product, which again await tankers, pipelines, and rail cars. After all the formidable reactors, furnaces, and towers, where crude oil has been given a good heating, the crucial stage arrives: final blending. This is no longer a turbulent boiling or flowing in pipes. It's like a chemical kitchen, where a complex dish with a taste of power and precision is prepared from a few simple ingredients. Each fraction obtained from previous processes has its own properties. One is light, volatile, with a low octane number. Another is heavier, dense, resistant to temperatures and pressure. From these, like from puzzle pieces, petrochemical technologists assemble the required mixture. This is called blending. And this is the moment when gasoline essentially is born. It is not mixed randomly. Everything happens according to precisely calculated formulas. The fractions are fed into mixing tanks, where every drop is controlled by automation. Machines know exactly how much of what to supply to get the desired grade of gasoline at the output, with a certain octane number, resistance to detonation, and stability during storage. But even the most precise mixing is not the end. Special additives are added to the gasoline composition. These are small in volume, but powerful in effect substances. It is they that help the fuel work better, not destroy engines, not rust in tanks, not evaporate too quickly, not clog injectors, not pollute the atmosphere. Additives are introduced in microscopic doses, literally a few ounces per gallon, but modern fuel is impossible without them. When everything is ready, the gasoline goes into finishing tanks. These are giant steel containers located next to railway lines, truck ramps, and port pipelines. There, the fuel can be stored for days or weeks, waiting for its time. Then, shipment, tankers, rail cars, barges. And so, the fuel hits the road. Maybe this very batch of gasoline will be hissing in the tank of your car in a few days. Maybe it will power a combine, a truck, a boat, or an airplane. But whatever the case, this gasoline has come a long way. From dark, raw mud to perfect, transparent fuel. It is clean, stable, ready to burn, but only when you say, "Start your engine."